Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics and the chapters of mechanical actions and equilibrium of a body. This exercise was a previous one in the brevet exams in 2017 second session, exercise number 2. The title of this exercise is equilibrium of a solid. A spring R perfectly elastic has a stiffness K is equal to 10 newtons per meter. Then what does K represent? In order to compress or elongate the spring by 1 meter, we need to apply a force worth of 10 newtons. This spring is fixed at its upper end O to a support A. A solid S of mass M is equal to 100 grams. So knowing that grams is not the SI unit of mass, in order to convert from grams to kilograms, we divide by 1000. Then 100 divided by 1000. So the mass is given by 0.1 kilograms. Is suspended to the lower end A of R as shown in document 2. They mentioned document 2. Then now we can use it. S is at equilibrium. So for the rest of the exercise we can use the condition of equilibrium and take G is equal to 10 newtons per kilogram. Now the trick in solving such type of exercises is to determine whether the spring R is being elongated, undergoes elongation or compression. So here it's obvious that the spring R undergoes elongation because from the free end of the spring A is being attached, we attach a solid S, so the spring R undergoes elongation. And in this case, in the case of elongation, the elongation delta L is given by the final length minus the initial length. Now number 1, S is submitted to two forces, its weight W and the tension T of the spring. 1.1. Reproduce the figure of document 2 and represent these forces without a scale, and by represent we mean it's meant to draw the forces W and T. So this is the solid S. And let's suppose that this is the point G, which corresponds to the center of gravity of the solid S. And this is the point A, which is the point of contact between the two bodies that are at interaction, and they are given by the solid S and the spring R. Then the two forces acting on the solid S are the weight. Then the weight acts vertically downward. Now here the length of the vector W is not important because they are telling me represent without a scale. So the weight is classified as an action at a distance, so the point of application of W will be G and it acts vertically downward. Now as for the tension T, because it is classified as a contact force, so its point of application will be the point of contact A and it is vertically upward along the spring. But here the important thing is that the length of W and T must be the same because the solid S is at equilibrium, so both forces will have the same magnitude. Now 1.2, tell for each of the two forces whether it's a contact force or force acting at a distance. We know that the weight, so the only forces that act at a distance are the weight, the electric and the magnetic. So this force is acting from a force, let's say acting at a distance, and all other forces are classified as contact forces, and in particular the contact, the tension T, so it is a contact force. And now in 1.3 they are telling me to calculate the magnitude W of W vector. So here we have the mass and we have the value of G, then W, which correspond to the fourth property of the vector W. W can be calculated using the following formula, M multiplied by G. Now the value of M is given by 0.1 and the value of G is given by 10. Plugging this on the calculator, it will give me 1. Since both M and G are in the SI, so the value of W will be in the SI, which is in newtons. Then W is equal to 1 in newtons. Now in 1.4, show that the magnitude T of T vector is 1 newtons in this case. So in this case, it means that we need to use the condition of equilibrium. Notice that here the tension T can be calculated using Hooke's law. We know the stiffness K, however we don't know the elongation delta L. Therefore, let's use the condition of equilibrium to determine the magnitude of the tension T, because we already know the magnitude of the weight. So we always start by writing at equilibrium. Now, how do you apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by the weight plus the tension vector. And on the other side of this vectorial equation we write the zero vector, and we don't forget the vector over the zero because this is a vectorial equation. Now moving T to the right hand side, W will be equal to minus T vector. Now the first equation tells us that the forces acting on the solid S given by the weight and the tension, the effect of these forces cancel each other to give us the zero vector corresponding for the equilibrium, whereas the second equation tells us that both forces have the same line of action, the minus sign is for the opposite direction, and the equal also for the same magnitude. Here we are interested in calculating or determining the magnitude of the tension, so let's say in magnitude. Now we drop down the vectors and we remove the minus sign, we'll get that W is equal to T, but we already know from 1.3 that the value of W is given by 1 Newton. Then in this case, T is equal to 1 Newton. Now we are in part 2. The initial length of R is L0 is equal to 20 centimeters. Knowing that centimeters is not a unit of length, in order to convert from centimeters to meter, we divide by 100. Then 20 divided by 100. So this will give us that the initial length of the spring is given by 0.2 meters. So what does this initial length represent, or the free length? This represents the length of the spring before we connect the solid S. So L0 is equal to 0.2 meters. So this length represents the free length of the spring, or the initial length, before we connect the solid S to the spring. Now in 2.1, determine in centimeters the elongation delta L of R. So here the elongation delta L can be determined, for example, from this equation, because we know the value of L0 to be given by 0.2 meters. However, we don't know the final length of the spring. Therefore, we cannot use this equation in order to determine the elongation delta L. However, because we know the stiffness K, and we know that the tension in the spring now in this case is given by 1 Newton, then we can apply Hooke's law to R. So let's say apply Hooke's law. Hooke's law is given by T is equal to K multiplied by the elongation, which is given in this case delta L. Now constructing the triangle of this formula. Here, because we have multiplied and T will be at the top, K and delta L are at the bottom. Knowing that we are interested in calculating the value of delta L, putting our hand over delta L, so delta L will be given by T divided by K. Now the value of T is given by 1 and the value of K is given by 10. So T and K are in the SI, so the value of delta L will be in the SI, which is 0.1 meters. But here notice that they are telling me determine in centimeters. So delta L is equal to 0.1 meters. And in order to convert from meters to centimeters, we simply multiply by 100. Then 0.1 multiplied by 100. So it will give us 10 centimeters. So the elongation delta L is given by 10 centimeters. So what does delta L represent? So as we have said that the free length of the spring is given by L0 is equal to 20 centimeters. So when we attach the solid as, the spring will elongate. So this is the solid as. Now the elongation of the spring is given by, so the spring will elongate by delta L is equal to 10 centimeters. Now in 2.2, they are telling me deduce the final length L of R, and by deduce it means that we need to use the part just previously before. In part 2.1 we have determined in centimeter the elongation delta L. So we know the value of delta L and we already have the value of L0, so we can deduce the final length L of R using this equation. So here the final length is denoted by capital R. So delta L is equal to L minus L0. Knowing that we are interested in calculating the value of L, the value of delta L in centimeters is given by 10, and the value of L0 is given by 20 in centimeters. So what is the type of this equation? It is linear equation and one unknown, which is L. So how do we solve this equation? We put L on one side and all the other numbers on the other side. So L is given by 10. Sorry, let me make this clear, that this is 10 and not L0. So, and moving 20 to the other side, then L will be 30. Since both delta L and L0 are in centimeters, so the value of L will be in centimeters. So here in 2.2 they didn't specify that the unit of L, so let's convert this back to meters. So in order to convert from centimeters to meter, we simply divide by 100. Then the final length of the spring is given by 0.3 meters. Okay. Let me make some space here. And now in number 3 they are telling me that R can be elongated to a maximum value delta L max is equal to 15 centimeters. So dividing by 100, so the maximum elongation that the spring can undergoes is given by 0.15 meters. Without losing its elasticity, determine then the maximum mass and max that could be hung at A. So in order to determine the maximum mass and max, we need to determine the maximum weight, because we know that weight is equal to mass times gravity. So M will be given by W divided by G. So in order to determine M max, we need to determine W max. And W max can be determined from T max, because we know that the tension now in this case is equal to W, because the solid S is at equilibrium. And in this case, we can determine T max because we know the value of the maximum elongation delta L. So let's say apply Hooke's law. So T is equal to K delta L. Here T, so this will be T max because it is delta L max. Now the value of K is given by 10 and the value of delta L max is given by 0.15. Plugging this on the calculator, it will give me 1.5. Since both K and delta L are in the SI, so the value of T will be in the SI, which is in newtons. So now T max is equal to 1.5 in newtons. But we know that from part 1.4 that W is equal to T, but T max is equal to 1.5 in newtons. Then in this case, W max is equal to 1.5 in newtons. So, and we know that W is equal to M multiplied by G, and we don't forget that we need to determine the maximum mass. So constructing the triangle of this formula, W at the top, M and G are at the bottom. We are interested in calculating the value of M, which is M max. corresponding for W max divided by G, and the value of W max is given by 1.5 dividing by the value of G, which is 10. Now plugging this on the calculator, it will give me 0.15. Since both W and G are in the SI, so the value of M will be in the SI, which is kilograms. So M max that could be attached to the spring without losing its elasticity is given by 0.15 kilograms. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.